Modelling curves. There are two types of relationship that we are going to explore in this lesson. One of them is the relationship between an x and y variable, which is of a power format. For example, something of the form y equals k x to the power of n. So, for instance, y equals 3x squared, y equals 4.5x to the power of 3 over 2, etc. So we can see that the variable x is being raised to a power in each of these cases. The other type of relationship that we're going to explore is what we call an exponential relationship. So, for example, a relationship of the form y equals k a to the power of x. So this time, the variable is the power. So for instance, y equals 4 multiplied by a half to the power of x. And again, we can clearly see that this is an exponential relationship because x is the power rather than the base. So in a power relationship, our variable x is the base. We can see that clearly here. But in the exponential relationship, x is the exponent, which is another way of saying power. We can see that there. So we're going to look at two examples to illustrate this idea of modelling a relationship. We're going to start off by looking at relationships of the form y equals kx to the power n. So what we might call a power relationship. X is the base that is being raised to a power. Here we have some data. It shows how the price p pounds of hiring a boat varies with the time over which it is hired in hours. Now, the first thing that we can do is plot these points to observe any patterns in the data, and you can see the points plotted on this set of axes here. You can have a go at joining up the points or drawing a curve of best fit through them, and it appears to have a sort of a power shape to it. It could be part of an x squared or an x cubed or another power of x type of curve. So it is thought that the relationship between the two variables is of the form p equals kt to the power of n. So p, of course, is on the y-axis, t is on the x-axis, and k and n are constants, which we're going to try and find. So how are we going to find these constants? Well, we're going to do something which is called reducing a relationship to linear form. So we start with the relationship p equals kt to the power of n. Remember that p effectively represents what's on the y-axis, and t effectively represents what's on the x-axis, and k and n are constants that we're going to try and find. So we're going to use logarithms to convert this into a linear format. Now, we can do this with logarithms of different bases, but it's often simplest to work in log to the base 10, or log, as it's also written. So we're going to take a log of both sides. So log p equals log of kt to the power n. Now, this is a product of k and t to the power n, so I can split up the right-hand side into two logs. So I've got log of p equals log of k plus log of t to the n. And then I can use another log rule to bring this n down to the front here. And this then gives me log of p equals log of k plus n multiplied by log of t. Now, just for clarity, I'm going to rewrite this slightly. So log of p equals, I'm going to write the n log of t first plus the log of k. Now, you may start to realise that this has the format of a straight line. It has the form of y equals mx plus c. Let's match things up. So log p matches up with y. Remember, p is a variable which was originally represented on the y-axis. Log t matches up with x. N, which is something we're trying to find, matches up with m, and that leaves log of k, which matches up with the y-intercept, c. So what we can do is plot a straight line graph. And the straight line graph that we're going to plot is a graph of log p on the y-axis versus log t on the x-axis, and we can then use this line to find the values of n and k, because think about how we've matched everything up. Log p is on the y-axis, log t is on the x-axis. So for this graph, which we're plotting, of log p equals n times log t plus log k, n must be the value of the gradient. So if we find the gradient, we've then got our value of n, which remember was the original power up here. And log k is equal to the y-intercept. So if we find the y-intercept, this is equal to log k, and we can then do 10 to the power of the y-intercept to work out what k is, which then gives us this value here. And we've then been able to find the k and n constants, which allow us to fit together the equation of the curve, which matched the data when we plotted p versus t. So here's the information we need. I've added 2 layers to our table, so as well as the data for t and p, we've got the data for log p and log t. We then plot a straight line graph with the log p values on the y-axis and the log t values on the x-axis, and you can see a screenshot of this graph here. Now, the first thing we're going to do is find the gradient of this graph, which we know is equal to n. So I'm going to pick 2 points which we can see very clearly. Now this point here has an x-coordinate of 1.1 and a clear y-coordinate of 3. And this point here has an x-coordinate of 0.1 and a y-coordinate of 0. Pick points as accurately as possible and do not use any of the values from the table. Use the line of best fit that you should have drawn to match the points as closely as possible. So our gradient is equal to 3 minus 0 over 1.1 take away 0.1. So in this example, the gradient works out to be perfectly 3. Now remember, this is equal to n. Now our y-intercept is equal to negative 0.3. And if you remember from the previous work we did, the y-intercept is equal to log of k. So in order to find out what k is, we need to solve this equation. K is equal to 10 to the power of negative 0.3, and if we work this out, this is 0.501187, etc. So 0.501 to 3 significant figures. So what we have done is take a graph of log p equals n multiplied by log t plus log k, and we found the gradient and we've used it to find our value of n. We've found the y-intercept and we've used this to calculate our value of k. And if you remember, the whole idea was that we started with a curve which looked like that, and the curve was p versus t. And the relationship for this curve was p equals k multiplied by t to the power of n. By reducing this to a linear format and plotting the graph of the straight line, we were then able to calculate the values of n and k that we needed, and we can put these back into the equation of the curve now. So p equals 0.501 multiplied by t to the power of 3. Now we can check how accurate our work has been. For example, if we pick this value of t and this value of p and we substitute them into this relationship here, p would then equal 0.5011 ... and I'm going to use the full accuracy for here, having stored this in a memory, multiplied by t, which is 20 to the power of 3, and we find in our calculator, if we substitute this in, we get 4009.497, which is not a bad estimate for 4,000. So, having looked at how we can model with power relationships, for example, where x is the base being raised to some numerical power, let's have a look at exponential relationships and see if we can do something similar. So this is the second main example of what we're going to have a look at. And we can see clearly that if we're dealing with these sorts of relationships, x is the exponent, x is in the power, so this is an exponential relationship. Now, we're going to look at some data which shows the thickness of a glacier measured every 5 years from 1960 to 2010. So our x variable represents the number of years since 1960, and our y variable represents the reduction in thickness since 1960 of the glacier measured in metres. Now, the first thing that we're going to do is have a look at a plot of the original data. Now, y, if you remember on this particular example, represents the reduction in thickness, and the x variable represents the number of years after 1960. We can have a look at sketching a curve of best fit through the points. It's not quite as close a fit as in the previous example, but we do get quite a nice curve through there. Now this time, we think that the relationship between the two variables is of this format. So y this time is very clearly the reduction in thickness, x is the number of years after 1960, but we have some constants. Now, 10 is the base, so we are actually given the base in this example, but a and b are constants. And our aim is to find the values of a and b by doing something similar to the last example, where we reduce this to a linear format, plot a graph, and see if we can find the values of a and b from the straight line graph that we're going to use. So our first job is to reduce this exponential relationship to a linear format by taking logs of both sides. So again, we're going to work with log to the base 10. So I'm simply going to write down log of y equals log of, brackets, a multiplied by 10 to the power of bx. Now, here's the product on the right-hand side. So the left-hand side can remain the same, but the right-hand side I will split up into log of a and then plus log of 10 to the bx here. We can then use another log rule to move this bx to the front here. So we get log y equals log a plus bx multiplied by log 10. But remember, we're working in base 10. So log to the base 10 of 10 is simply equal to 1. So this whole relationship can be written as log y equals log a plus bx. Now, as we did last time, I'm going to rewrite this, just reordering things slightly. Log y equals bx plus log a. And the eagle-eyed amongst you will hopefully have noticed that this takes the format of a straight line graph. Y equals mx plus c. Let's compare everything. Log y represents the y-axis. X is itself representing the x-axis. B represents the gradient, and the y-intercept is log a. So just as we did last time, we can match up everything that we need. And our aim this time is to use this result here and plot a graph of, this time on the y-axis, log y, but this time on the x-axis we will plot x. As you can see from the format, x is just x here. Now, the straight line graph that results, we can find its gradient. And as you can see from the matching we did just now, the gradient must equal b. We can also find the y-intercept, and the y-intercept will equal log of a, which means, of course, a will equal 10 to the power of the y-intercept. This will then give us the values of a and b that we need to substitute back into this result up here and work out the equation that we are going to model our data with. So here's the data that we needed. If you recall, on the y-axis, we're going to plot log of y. So these values have now been calculated. On the x-axis, we are still just going to plot x, so we don't need to alter the x data at all. So here is a plot of our data values, and a line of best fit has been drawn through these. It's not a perfect fit as it was with the first set of data. This is more likely to be a realistic set of real life data, and the line of best fit is never usually going to perfectly fit all the data points, but still it's a good close fit with most of the points very, very close to the line. So remember, we have a straight line which has the equation log y equals bx plus log a. So b is simply equal to the gradient. So let's pick some points that we can find. So that's quite a clear-cut point there, which would have a coordinate of 42, 1. Let's find another point which intersects a coordinate clearly. So this is clearly the point 22, 0.4. Try and make your right angle triangle as large as possible. The larger that you can make it, the less error there will be in your result. So here's delta y, here's delta x. Let's calculate the gradient. So the gradient, which we know is going to be equal to b, is delta y over delta x, which is equal to 1 take away 0.4 divided by 42 take away 22, and this will give us our gradient. And this works out very neatly to be 0.03. So this is our value of b. Now the y-intercept is a little bit less clear, so we're going to have to estimate this a little bit. So the y-intercept is equal to negative 0.25 approximately. And of course, this is equal to log a. So we know that log to the base 10 of a is equal to negative 0.25. A will therefore equal 10 to the power of negative 0.25. And let's work this out. And this comes to a value of 0.56234 ... 0.562 to 3 significant figures. Although again, I'll save that in a calculator memory in case we need it. So what have we done? We have found out that our original data, if you recall, we had data of y versus x, which seemed to have some sort of curved shape to it. And we were told that the data could be modelled with an equation of the form y equals a multiplied by 10 to the power of bx. We then converted this exponential equation here into a linear format, and we plotted a graph of the linear data, so the log y versus x graph, which is this graph over here, and we found the gradient of this graph, which gave us the value of b as 0.03. We then found the y-intercept of our straight line, which allowed us to work out the value of a. So we can now fit this information together, and this gives us y equals 0.562, there's our a value, multiplied by 10 to the power of 0.03x. So to be really clear, here is b, 0.03, and here is a, rounded to 3 significant figures. And this is a model of the equation for our data points. Remember the data points as we plotted them. They weren't perfect. Some of them were sitting on our curve, some of them were above, some of them were below. So this is a possible equation that could be used to model a curve that we want to fit to our data points. Now, why might we want to do this? Well, I might want to know what is the thickness of the glacier in 70 years' time. I might want to predict what the thickness of the glacier is well into the future, and what I might try and do is use this equation to model future events. So let's summarise what we know so far. We have looked at 2 different kinds of relationship. We have looked at a power relationship, so something of the form y equals kx to the power of n. And we have also looked at exponential relationships. For example, y equals k a to the power of x. These are the general formats. They can be adjusted slightly. For instance, in the last example, there was another constant b multiplying the x in the exponential relationships, but these are some of the most basic formats. So, important to know what's a variable and what's a constant. So y here is a variable, of course so is x, and in this case here y and x are variables as well. K and n are constants, as is a. So first thing we do is to look at how we reduce to linear form. So let's start by taking logs of both sides. So we have log y equals log of kx to the power n. Log y equals log k plus log of x to the n. Log y equals log k plus n log x. And for clarity, log y equals n times log x plus log k. And this is our linear format. Now let's match that to the equation of a straight line, y equals mx plus c, and let's make sure we understand which piece is which. So let's make it very clear that log y represents the y-axis, that log x represents the x-axis, and that the gradient of our straight line will give us n, and the y-intercept will give us log k. So when we plot a graph for our straight line, the graph will need to have on the y-axis log y and on the x-axis log x, and then we can observe the resulting straight line. Now, how do we then find the constants that we are looking for? So in this case, we need to find the values of n and k. So we can see very clearly from here that n is the gradient. So we work out the gradient of our straight line, and this is equal to the value of n. Now, our y-intercept here is equal to log k. Log to the base 10 of k. So to find k, we simply reverse this and calculate 10 to the power of the y-intercept. And this is how we reduce to linear form and find our constants k and n for a power relationship. Similarly, for the exponential relationship, let's take log to the base 10 of both sides. So log y equals log brackets ka to the power x. Log y equals log k plus log of a to the power x. Log y equals log k plus x log a. And I'm just going to rewrite that for a little bit of clarity. Log y equals log a multiplied by x plus log k. And let's compare that again with y equals mx plus c. So what can we match up? This time, log y is now the y variable. X is now the x variable. The gradient of the straight line that we will produce is equal to log a, and the y-intercept of the straight line that we produce is equal to log k. So it's important to make sure that we draw the correct kind of straight line graph. So remember what the variables were. The y variable is now log y, but the x variable is still x, and we will get some form of straight line from this. Now, how do we then find our missing constants, which are, of course, a and k, to substitute back into the original equation? Well, the gradient, m, is equal to log a. So we can then use this to work out a by doing 10 to the power of the gradient. And the y-intercept, we can see from here, is equal to log k, which means again we can work out k by calculating 10 to the power of the y-intercept. Now, it's important to realise that examples will vary in different ways. In the previous example, where we actually worked it out, we had the value of a, it had a base value of 10, and the other unknown was the multiplier of x, the coefficient of x in the power, the b value. So questions will vary ever so slightly, but what you need to be able to do is work through this technique. You will be asked to potentially do this in exams, and it's important that you can start with a power or an exponential relationship and reduce it to a linear form using these steps here. It is absolutely crucial that you can match up the components of the new straight line function and the original graph here. So this stage here where we show the very clear matching, that's also important. You've got to be able to plot graphs accurately, both on your graphical calculator and on paper, and you've got to be able to do readings from graphs as precisely as possible. So remember, when you're calculating the gradient, try and make your right-angled triangle as large as possible, and don't use data points from the data table. So use the line of best fit to identify 2 points which are hopefully far apart from each other. Lastly, you've then got to be able to interpret your results for the gradient and the y-intercept, which then allows you to calculate these missing constants. Once you know what these are, you can numerically go back and substitute them into your power or your exponential equation, and this will give you the equation that you can use to model your data. Once you have that equation, you might then be asked to do various calculations with that equation. So this leads us nicely into an example. We have a table of data which shows population data for a country. We have years from 1969 through to 2009, and we have the population in millions. Now, here's a nice example. We could plot a graph for this data, and we might want to then know what the relationship between the two variables, in this case t and p, is. We suspect that we could model it with an exponential model. So here we have an example, but we don't know what these constants are. So we don't know what A is, and we don't know what K is, but we predict that it's 10 to the power of KT. So what we're going to do is reduce this to linear form and then investigate what happens from there. So, part 1. Derive an equation for log to the base 10 of p in terms of a, k and t. Now, because there is a 10 in the model equation here, this will explain why we're using log to the base 10, although it is a convenient logarithm to use. And I think for clarity, the question has defined this as log to the base 10 to avoid any ambiguity. So, taking log to the base 10 of both sides, we will stick with the notation that we have been given in the question. That's log to the base 10 of p equals log of a multiplied by 10 to the power of kt. So, log to the base 10 of p equals log to the base 10 of a plus log to the base 10 of 10 to the kt. And we're allowed to do that because this is a product in the bracket which separates into the sum of two separate logarithms. Log to the base 10 of p then equals log to the base 10 of a plus, and we can pull this whole power down to the front like this, kt log to the base 10 of 10. But like last time, we know that that is equal to 1. Log to the base 10 of 10 is equal to 1. So we are left with log to the base 10 of p equals log to the base 10 of a plus kt. And we have fulfilled the brief of the question. So part 2 of the question asks us to complete the table and plot a graph of log p versus t. Remember, t is the number of years after 1960, and we have the information here. We're then going to plot the graph, which is going to have log p on the y-axis and t on the x-axis, and we're going to observe the straight line graph that we have. Of course, these values have been given to a high degree of accuracy. You will have to probably round these to 3, possibly 2 significant figures, depending on the level of accuracy of the graph paper that you have. You can also practice drawing the graph on your graphical calculator in stats mode and then using the techniques that you've used for scatter graphs in the statistics work to find the equation of the line of best fit that way. So here we have a pre-plotted graph of log p versus t. And the next thing that we're going to do is, of course, having drawn our line of best fit, use this to find the missing constants. So let's just go back to the equation of our straight line. the reduced linear form. This was log p is equal to log a plus kt, or log p equals kt plus log a. And of course the logs were to the base 10. Let's compare this to y equals mx plus c, and we can do the comparison that we've done previously. On the y-axis we have log p, on the x-axis we have t. The gradient of this straight line is equal to k, so I'm going to write that down. And the y-intercept is equal to log a. I'm going to write that down as well. So our y-intercept, or c value, is equal to log to the base 10 of a. So our first job is to find the gradient. So we're going to choose 2 points which cross over in neat places where we can read the coordinates easily, and we're not going to use any of the actual data points to do this. We're going to use other points on the line of best fit because this will reduce the error. So as you can see, I've drawn my right angle triangle here. My gradient, or m, is equal to change in y over change in x. So using the coordinates carefully, I can see that is 2.2 subtract 1.8, the difference in y coordinates, divided by 46, take away 11, the difference in x coordinates. And this gives us 0.011428, etc., which I will round to 0.0114 to 3 significant figures, and I'm going to store this in a calculator memory should we need to use this again later on. So now to find the y-intercept, where we do have to estimate a little bit, and we can see this is just under 1.7. So the y-intercept is equal to probably about 1.68, and we are estimating a little bit here. So of course the y-intercept is equal to log to the base 10 of a, so log to the base 10 of a equals 1.68, and we have to solve this little equation. A equals 10 to the power of 1.68. So now we have to fit this information back together and express p in terms of t. So if you recall, the original equation, which we were using to model the data, was p equals a times 10 to the power of kt. So we can now write p equals a, which is 10 to the power of 1.68, multiplied by 10 to the power of 0.0114t. We might potentially be asked to combine these two terms, so 10 to the 1.68 plus 0.0114t overall. But both versions are indeed correct. Question 4. According to the model, what was the population in 1960? So of course, t is the number of years after 1960. T equals 0. So this gives us p equals 10 to the power of 1.68 multiplied by 10 to the power of 0, which is just 1. So this gives us a population value of 47.8630 ... or 47.9 million to 3 significant figures. So we've used our model, the equation for the set of data that we have, to estimate the population for a time which isn't included in the original set of data that we are basing our calculations on. So you might be asked to decide whether or not that is an accurate process. Because we've used data from 1969 through to 2009 on which to identify our equation, is it valid for us to go back to 1960? Part 5. According to the model, when will the population reach 200 million? So we're saying that our p-value is 200, and this equals 10 to the 1.68 multiplied by 10 to the power of kt, and we're going to use our exact calculator stored version of k. So let's divide by 10 to the 1.68 first of all, and this gives us 4.178, etc., equals 10 to the power of kt. Now we're then going to take log to the base 10 of both sides. So log to the base 10 of 4.178 ... equals kt, because of course log to the base 10 cancels out 10 to the power of. And then divide by the value of k that we have stored in our calculator for full accuracy, and this then gives us our value of t. So t equals 54.3401 ... So 54.3 years. Now, of course, t represents the number of years after 1960, so we're saying 54.3 years after 1960, which gives us the year 2014. And again, we're making a prediction about a year which is outside the range of data that we have been given, and we have to come to a conclusion about whether it's valid to do that, because we don't know that the exponential relationship that we have actually works outside of the data set on which it is based. So to finish off, we're going to discuss how we could do this reduction to linear form using the natural log function ln rather than log to the base 10. All of this would work in any base, but log to the base 10 and log to the base e, i.e. the ln function, are the most commonly used forms of logarithms. So we're going to take ln of both sides here. So ln of y equals ln of kx to the power a. I'm starting with a very simple power relationship. Let's now simplify the logs on the right-hand side. We can see we've got a product here. So ln of k plus ln of x to the power a. And again, ln of y equals ln of k plus, and we can pull a down to the front, a ln of x. As you know, it's nice to do a little rewrite. So a ln x plus ln k is equal to y. And then straight away we can see y equals mx plus c. The y-axis is represented by ln y. The x-axis is represented by ln x. The gradient of the straight line is a, and the y-intercept is ln k. Now, let's see what would happen if we had a relationship of the form y equals ka to the power of x. Again, ln y equals ln of ka to the power of x. ln y equals ln k plus ln a to the x. ln y equals ln k plus x ln a. And then let's just do a little bit of rewriting. So ln y is equal to ln a multiplied by x plus ln k. And again, comparing to y equals mx plus c, we can very clearly see that ln y goes on the y-axis, x goes on the x-axis, the gradient is ln a, and the y-intercept is ln k. So everything that we've done in log to the base 10 could have been done using the natural log function as an alternative, and you will come across many different questions which require you to do either of these formats.